Hello everyone, welcome to Neso Academy. We are learning theory of computation, and in the previous lecture, we have understood the partitioning algorithm for DFA minimization. And now in this lecture, that is partitioning algorithm solves problem. We are going to solve and understand one problem on partitioning algorithm. So the topic for this lecture is partitioning algorithm. Let's read our problem statement. Construct a minimum state automaton equivalent to the given DFA. That means this is the DFA given to us. I hope this diagram is not frightening you. So this is the DFA given to us, and as per the question, we need to construct a minimum state automaton equivalent to this DFA. Minimum state automaton means minimized DFA. So we have to create the minimized DFA of this DFA by applying the partitioning algorithm. So this is the DFA given to us, and before applying the partitioning algorithm, let's first convert this transition diagram of DFA into its corresponding transition table. Because I have explained you that transition table is much more simpler to understand. So this is the transition table corresponding to this transition diagram of DFA. And I hope you all know how to make this transition table. Now we are all set to apply the partitioning algorithm. So what was the first step for partitioning algorithm? The first step is to remove all the unreachable states from our DFA. Unreachable states are those states that cannot be reached from the initial state of the DFA. So now we have to check all the states, and we need to check whether they are reachable or unreachable from the initial state. The initial state of the DFA is Q0. Let's check our first state, which is Q1. We can clearly see that we can reach from Q0 to Q1 using this transition, which means Q1 is a reachable state. Let's check Q2. We can reach from Q0 to Q2 using these two transitions. That means Q2 is also a reachable state. Now let's check Q3. So can we reach Q3 from Q0 using any path? No. If you clearly observe, there is no path from Q0 to Q3. That is why Q3 is going to be our unreachable state. Now let's check Q4. So these two transitions cannot lead to the state Q4 because this is an outgoing transition. So let's check whether there is any other path from which we can reach Q4 from Q0. So following this transition, then this one, we can reach Q4, which means Q4 is also a reachable state. Now let's check Q5. So using this transition, we can simply reach Q5 from Q0. Let's check Q6. So Q6 can be reached from Q0 using these two transitions also. And you can also reach Q6 using these two transitions. That is why Q6 is also a reachable state. Now let's check Q7. So you can reach Q7 from Q0 using these transitions. So this is the path from Q0 to Q7, which means Q7 is also a reachable state of this DFA. So we can conclude that Q3 is the only unreachable state of this DFA. So we need to eliminate the unreachable state, which is Q3. So we have to eliminate the Q3, and as we have eliminated the Q3, we also need to eliminate all the transitions of the Q3. So we need to eliminate this transition. Also, we need to eliminate this transition. Now Q3 is eliminated from our DFA. But in the transition table also, Q3 is there. So we need to eliminate the row of this table corresponding to the state Q3. So we have to eliminate this row from our transition table. So Q3 is an unreachable state. That is why we will eliminate Q3 from this diagram as well as the transition table. So in the last lecture, we have solved the category of DFA minimization problem in which there was no unreachable state, but there were multiple final states. And this is the category of question in which there is an unreachable state, but there is only one final state. So now this is the transition table of our DFA in which there is no unreachable state Q3. Now what we have to do the next? In the next step, we need to find out the value of zero equivalent. What is zero equivalent? It is the set containing only two partitions. The first partition will contain only the non-final states, and the second partition will contain only the final states of our DFA. So let's see the value of zero equivalent. Zero equivalent, or we can call it as zero equivalence partition, represented by pi naught, will be equal to two partitions. The first partition is containing only the non-final states of this DFA, and the second partition is containing only the final state of this DFA. As you can clearly see, Q2 is the only final state of this DFA. So it has been placed under the different partition. And Q0, Q1, Q4, Q5, Q6, Q7 are all the non-final states of this DFA. So they have been placed under the same partition. So this is the zero equivalence partition. And now we need to calculate the 1 equivalence partition, 2 equivalence partition, 3 equivalence partition, and so on till we reach a point where no further partitioning is possible. So let's start with 1 equivalence partition or 1 equivalent. While calculating 1 equivalence partition, we need to consider 0 equivalence partition. For each partition, we need to check each pair of states. If the states are equivalent, we will place them under the same partition. But if they are distinguishable, we will separate them into a different partition in 1 equivalence partition. So let's start with our first pair of states, which is Q0 and Q1. So we are taking Q0 and Q1. 1 equivalence partition is represented using pi 1, which will be equal to, we need to check Q0 and Q1. On input symbol 0, Q0 gives Q1 and Q1 gives Q6. Q1 and Q6. Q1 and Q6 lies in the same partition. Let's check for the input symbol 1. Q0 is giving Q5 and Q1 is giving Q2. Q5 and Q2. And you can see Q5 and Q2 lies under different partitions, which means Q0 and Q1 are not equivalent to each other. Q0 and Q1 are distinguishable states. That is why we cannot place Q0 and Q1 under the same partition. So, our first partition will contain Q0 and Q1 will be separated from this partition. So, there will be a new partition containing Q1. Now, let's check our next state, which is Q4. Now, Q4 is to be checked with Q0 as well as Q1 because Q0 and Q1 are not equivalent to each other. So, let's check Q4 with Q0. So, this time we are considering the states Q0 and Q4. Now, Q0 on 0 gives Q1 and Q4 on 0 gives Q7. So, we are getting Q1 and Q7. Q1 and Q7 lies under the same partition. Now, Q0 on 1 gives Q5 and Q4 on 1 gives Q5. Q5 and Q5 lies under the same partition, which means Q0 and Q4 are equivalent to each other. If Q0 and Q4 are equivalent states, we need to place them under the same partition. So here along with Q0, we have to write Q4 also. But we cannot place Q4 with Q1 because Q0 is already distinguishable with Q1. Now we need to check our next state, which is Q5. Now Q5 is to be checked with either of Q0 or Q4, and it is to be checked with Q1. So first we are considering the states Q0 and Q5. So the states that we are taking are Q0 and Q5. Now on 0, Q0 gives Q1 and Q5 gives Q2. So we are getting Q1 and Q2. Now Q1 and Q2 lies under the different partition, which means Q5 is not equivalent to Q0 as well as Q4. This means now we need to check Q5 with Q1. So the states that we are considering this time are Q1 and Q5. Q1 and Q5. On 0, Q1 gives Q6 and Q5 gives Q2. So we are getting Q6 and Q2. Q6 and Q2 also lies under the different partitions, which means Q5 is not equivalent to Q1 also, which means we cannot place Q5 with Q1 also. That means we need to create a separate partition for the state Q5. Now we are done with the states Q0, Q1, Q4, Q5, and the next state is Q6. Now Q6 is to be checked with either of Q0 or Q4, and Q6 is to be checked with Q1, and Q6 also to be checked with Q5. So first, let's check Q6 with Q0. So the states that we are considering this time are Q0 and Q6. So we are taking Q0 and Q6. So Q0 on 0 gives Q1 and Q6 on 0 gives Q6. So we are getting Q1 and Q6. Q1 and Q6 lies under the same partition. Now for input symbol 1, Q0 gives Q5 and Q6 gives Q4. So we are getting Q5 and Q4. Now Q5 and Q4 lies under the same partition, which means Q6 is equivalent to Q0 and Q6 will also be equivalent to Q4. So we can place Q6 under this particular partition. And now we don't need to check Q6 with Q1 and Q5 because Q1 and Q5 are already distinguishable from this particular partition. So now we have to move further to the state Q7. Now Q7 has to be checked with these three states, or we can say any one of these three states, because these three are equivalent to each other. And Q7 is to be checked with Q1 and Q5. Let's first check Q7 with Q0. So this time we are checking Q7 with Q0. On 0, it is giving Q1 and Q6. Q1 and Q6 lies under the same partition. For input symbol 1, we are getting Q5 and Q2. Now Q5 and Q2 lies under the different partition, which means Q0 and Q7 are not equivalent to each other. So let's check Q7 with Q1. So we are considering Q1 and Q7. On 0, it is giving Q6 and Q6. Now Q6 and Q6 lies under the same partition. For input symbol 1, we are getting Q2 and Q2. Q2 and Q2 also lie under the same partition, which means Q7 is equivalent to Q1. So now, since Q7 is equivalent to Q1, we can write it along with Q1 under this particular partition. And now all the states of this partition are now completed. That means this partition is splitted into the three partitions. The three partitions are Q0, Q4, Q6 as one partition, Q1, Q7 as the second partition, and Q5 as the third partition. Now, we will check the next partition, which is Q2. Q2 is a single state in this particular partition, so it cannot be checked with any other state, which means we need to write Q2 as it is in the one equivalence partition also. So this is how we have completed one equivalence partition with the help of zero equivalence partition. Now we need to calculate two equivalence partition because the partitioning is not stable now. Pi 1 is not equal to pi 0. So we need to calculate pi 2 with the help of pi 1. Because pi 1 was calculated with the help of pi 0, that is why pi 2 will be calculated with the help of pi 1. So we need to consider all these partitions one by one, and we need to check all the pair of states, whether they are equivalent or distinguishable. So the first pair of states that we are taking is Q0 and Q4. So we are taking Q0 and Q4. On 0, it is giving Q1 and Q7. Now Q1 and Q7 lies under the same partition. Let's check for 1. Q0 gives Q5 and Q4 gives Q5. We are getting Q5 and Q5, which lies under the same partition. That means in two equivalence partition also, Q0 and Q4 are equivalent states, which means they will remain under the same partition. Now let's check for the state Q6. Q6 can be checked with either of Q0 or Q4 because Q0 and Q4 are equivalent to each other. So let's check Q6 with Q0. So we are taking Q0 and Q6. On 0, it is giving Q1 and Q6. Q1 and Q6 lies under the different partition, which means this time Q6 is not equivalent to Q4 and Q0. That is why we have to separate Q6 into a different partition. So we have separated Q6 into a different partition. Now we need to consider this particular partition containing the states Q1 and Q7. So we are taking Q1 and Q7. On 0, it is giving Q6 and Q6. Q6 and Q6 lies under the same partition. Now for 1, it is giving Q2 and Q2. Q2 and Q2 lies under the same partition, which means Q1 and Q7 are equivalent states. So in the two equivalence also, they will remain together in the same partition. Now we need to check the another partition, which is Q5. Now Q5 only has a single state, that is Q5 itself, so we cannot check it with any other state. So here we will write Q5 as it is. And same rule will be applied for the state Q2 also, because it also has only one state, which is Q2. This particular partition only has a single state Q2. That is why it cannot be checked with any other state. So this is the two equivalence partition or two equivalent. Now we need to calculate three equivalent. Why? Because as you can see, Q2 is not equal to Q1. This particular partition has been separated into two partitions. That is why the partitions are not stable now. So we need to calculate three equivalence partition also, which is represented using pi 3. Now, three equivalence partition will be calculated with the help of two equivalence partition. So we need to check all the partitions and we need to check all the pair of states. Let's start with the first pair, Q0 and Q4. Q0 and Q4. On 0, it is giving Q1 and Q7. Q1 and Q7 lies under the same partition. For 1, it is giving Q5 and Q5. Q5 and Q5 lies under the same partition, which means in the three equivalence also, Q0 and Q4 will lie under the same partition and they will not be separated because Q0 and Q4 are equivalent states. Now Q6, that is this partition, is only containing a single state. So we can write it as it is, that is Q6, because it cannot be checked with any other state. Now let's check Q1 and Q7. Q1 and Q7. On 0, it is giving Q6 and Q6 lies under the same partition. On 1, it is giving Q2 and Q2 lies under the same partition, which is this one. So these states are equivalent to each other, and in three equivalence partition also, we have to write Q1 and Q7 together. Now let's check this partition. As I have already explained you, this is a single state. So we can write it as it is, that is Q5, because it cannot be checked with any other state. And the same rule applies for the state Q2 also. So this is the three equivalence partition that we have got. And now you can clearly see pi 3, which is three equivalence partition, is same as 2 equivalence partition, which is pi 2. No splitting has occurred, which means the partitions are stable now. So, these are 0 equivalent, 1 equivalent, 2 equivalent, and 3 equivalent partitions. And we can say pi 3 is equal to pi 2. That is why partitions are stable now. And we have reached the point where no further splitting can occur. So this is the termination point of the partitioning algorithm. So we can say that the states of minimized DFA are Q0, Q4 combined together as a single state, Q6, Q1, Q7 combined together as a single state, Q5 and Q2. So these are the 5 states of our minimized DFA. And this is the transition table of our original DFA after eliminating the unreachable state, which was Q3. Now we need to calculate the initial and final states of our minimized DFA. The initial state of the original DFA is Q0. So the state containing Q0 is this one. So this will be the initial state of our minimized DFA. The final state of the original DFA is Q2. That is why this Q2 will be the final state of our minimized DFA. So this is the basic structure of the transition table of our minimized DFA. These are all the 5 states that we have just calculated. 0 and 1 are the input symbols. Now let's calculate the next states. Q0, Q4. So Q0, Q4 on 0 gives Q1, Q7. Q1, Q7 is already a state, so here we can write Q1, Q7. Now Q0, Q4 on 1. Q0, Q4 on 1 gives Q5, Q5. Now Q5 is already a state, so we can write Q5. Let's check Q6. Q6 on 0 gives Q6, so we can write Q6. And Q6 on 1 gives Q4. But Q4 is not a single state, so we have to write the state containing Q4. So we can write Q0, Q4. Now let's check Q1, Q7. Q1, Q7 on 0. Q1, Q7 on 0 gives Q6, Q6. And Q6 is a state, this one, so we can write Q6. Now Q1, Q7 on 1. So Q1, Q7 on 1. We are having Q2, Q2. Q2 is a state, so we can write Q2. Now Q5 on 0 gives Q2, so we can write Q2. And Q5 on 1 gives Q6, so we can write Q6. Now Q2 on 0. So Q2 on 0 gives Q0, so we have to write Q0, Q4. And Q2 on 1. So Q2 on 1 gives Q2, so we can write Q2. So this is the transition table of our minimized DFA. So now we need to construct the transition diagram of this transition table. So these are the 5 states of our minimized DFA. Q0, Q4 is the initial state and Q2 is the final state of our minimized DFA, while Q1, Q7, Q6 and Q5 are the regular states of our DFA. Now let's make all the transitions. Q0, Q4 on 0 gives Q1, Q7 and Q0, Q4 on 1 gives Q5. So we can make both of the transitions. Q6 on 0 gives Q6 and Q6 on 1 gives Q0, Q4. So for Q6 also, we can make both the transitions. Q1, Q7 on 0 gives Q6 and Q1, Q7 on 1 gives Q2. So for the state Q1, Q7, these are the 2 transitions. Q5 on 0 gives Q2 and Q5 on 1 gives Q6. So for Q5, we can make both of the transitions. Now for the state Q2, on 0 the next state is Q0, Q4 and on 1 the next state is Q2. So we can make both the transitions for the state Q2. This is the complete transition diagram of our minimized DFA. So this was the original complex deterministic finite automata with 8 states. And we have converted it into a minimized DFA, which is much simpler and only containing 5 states. So this is how we have solved a problem for DFA minimization using partitioning algorithm. In this way, we are done with our topic, partitioning algorithm. And from the next lecture onwards, we will begin with the second method of DFA minimization, which is Myhill-Nerod theorem, or we can call it as the table filling method for DFA minimization. So this was all from my side for this lecture. Thank you, and I'll see you in the next lecture.